Linear algebra part 3, and we start with number 2 of the series of Just the Math from chapter 9 from A.J. Hobson, which is about the operations you can do with matrices. Now, one operation he is not mentioning, which I would like to mention, is the addition. And let me quickly add that here. And in fact, that is really very simple. I have a matrix and another matrix, and I am adding them up by adding both of the first elements. 1 plus 5 equals 6, 2 plus 7 equals 9, and so on. This is also 9, and 4 plus 8 is 12. So we see that A plus B gives me a new matrix C. Now, what are the properties of this operation? Well, to have a look at that, I'm looking here. First of all, the associative law applies, which says that if I have a matrix A plus B plus C, and I first add B and C, the result is the same than in the case I first add A and B. Commutative law obviously is true as well. So that's okay. And the last property I would like to discuss was the question, is it a closed operation? Now, what was that again? Here we have the definition again. A set S, so in this case S contains all the matrices you can imagine, is said to be closed under binary operation, in this case addition, if both matrices are an element of S. Obviously they are matrices, and if I perform the operation, then the result needs to be an element of S as well. Now let's have a look. For instance, you can see that over here I have here matrix A, where the elements of A are an element of R. The same is true for B, and you see that again for C also all the elements are an element of R. So indeed this is a closed operation. Another operation I would like to mention is a multiplication by a scalar. For instance, here I have here a matrix A, which is multiplied by a number, and you see the effect because the elements of matrix B are simply the result of multiplication of the scalar times each element, 5 times 1, 5 times 2, and so on. This is a trivial operation. The third, more interesting operation is when I'm looking at the multiplication of two matrices. So what would the result be, the result of this? And in order to make this a little bit more imaginable, I'm looking at this illustration from Mr. Hobson. Suppose I have a motor manufacturer who has 3 separate factories, and he makes 2 types of cars, the standard and the luxury model. And in order to manufacture each type of cars, he of course needs material, and he expresses the amount of material in units, and he needs labor, also expressed in units. And both units cost each 300 pounds per unit. Now, in order to have an overview of how much each type of car needs, we have this table here. We have the standard model needs 12 units of materials and 50 units of labor, and for the luxury you can see that as well. And he is planning to split up an order of 1300 cars, 400 cars standard type and 900 luxury cars over the 3 factories. So factory A will produce 100 standard cars and 400 luxury, and so on and so forth. Now if you would have a look at that, of course you would like to know how much material you will have to deliver in factory A, B and C, and how much labor you have to plan. So for instance, to have a look at how much units material you need, now for 100 standard cars in factory A, you need 100 times 12 units material, because for one car you need 12, so for 100 you need 100 units. Plus for the luxury cars, which is 400 in number, you need 15 units of labor. Now the same of course is true for the factory B, so 200 standard cars times 12 units and 200 luxury cars times 15 units, and here of course 100 times 12 plus 300 times 15. So this is the material you have to ship to each factory. The same you can calculate for the amount of labor you have to plan. So for instance, in factory A, for the 100 standard cars you need to plan 15 units 15 units of labor, plus for the 400 luxury types you need to plan 400 times 20, and so on and so forth. So once you fill this out, you have another table, or if you wish, another matrix, and this looks like this, where you can see at the bottom of the screen how the matrix from the factories, which I tend to call F, and this would be then the matrix of the cars, are multiplied. Indeed, it is the matrix F times the matrix of the cars, and then this is the result. I call this R. Now very quickly have a few remarks about this. If you look at vectors, you see that vectors, for instance vector A of 1 over 2, could be viewed as a so-called row matrix, and for instance a vector B, column matrix, sorry, and a vector B like 3, 4 could be viewed as a row matrix. Now if I multiply these two vectors, you get in fact something similar as to the multiplication of the matrices, because again you have 3 times 1 plus 4 times 2, which again is 11. Now if you want to talk about matrices, in fact this is a 1 by 1 matrix, and according to a basic rule, it says that a 1-to-1 matrix is in fact simply the same as a scalar. So you see that the dot product of two vectors is indeed part of this multiplication of the matrices. Then another word about the order. We saw that the vector f had 3 rows and 2 columns. Vector c of the cars was 2 by 2. And indeed this multiplication only works if the number of columns is equal to the number of rows, otherwise it won't fit. And then again, the order of the matrix, the result matrix, is then this 3 times this 2. Okay, which brings me to my last point, and that's what that's about the commutative law. Would f times c equal c times f? Now there are several things that you could say about this. First of all, in our case, this wouldn't work, because if I look at the multiplication c times f, you would have a 2 by 2 matrix times a 3 by 2 matrix, and since these two, the number of columns and the number of rows, are not matching, this is not possible. So it is doubtful if the commutative law would work. And even if, for instance, it would work, then for instance the order of f would be, for instance, m rows and n columns. The order of c would be the opposite, and according to these numbers that would work, because here you would have the other situation the other way around, and at least from the numbers it would fit. And of course it would also fit if the matrices were squares, like for instance the matrix C, who had the same number of columns as rows, like for instance 12, 15, 12, 16 and 15, 20. But this example gives you an idea that even in that case the commutative law even then does not work. For instance, if I go back to the paper of Hobson, you see I have a vector A here times a vector B, which are squared vectors, and this is vector C, the result of the multiplication. If I change the order, you see the result is a different matrix. So, to cut the long story short, the commutative law does not apply. So if the commutative law does not apply, we should spend some time on looking on the other laws and see if they would work. Now I go back to the paper of Hobson, and we see, okay, for addition the commutative law works and the associative law works as well, and we already noticed that this is a closed operation. Then for multiplication the associative law works. The distributive law works as well, only the commutative law does not. And another question we would have to look at is this operation closed, yes or no? So let's have a look at that. Closed, yes or no? Which means that I have a vector, a matrix A and B, where the elements are an element of R, and obviously if I multiply them I have another vector, a matrix C, where the elements are also an element of R. So indeed this is a closed operation.